Hello, I'm Lou Bloomfield, and this is How Things Work. Today's topic, skating. When you're wearing skates, whether they're ice skates or roller skates, or simply something similar to a skate, like skateboard, your motion is especially simple most of the time. If you're at rest wearing skates, and I'm not wearing skates, so I'll use this can to illustrate life for a skater. When you're at rest, you tend to remain at rest. If you get pushed on, you tend to begin moving. On the other hand, if you're already moving, you tend to keep moving in a straight line, pretty steadily too. And in order to change your motion, something's got to push on you. So what we're going to be looking at is the behavior of objects that are not being pushed on and the behavior of objects that are being pushed on. The object in mind is a skater, but it applies to any object. So, to illustrate, to sort of examine all this stuff, let's start with the first observation that a skater at rest tends to remain at rest. So, why is that? And the answer is because. Because this is how our universe works. That objects that are sort of left alone and that are already motionless, at rest is physics jargon for not moving. So if it's already not moving, it tends to remain not moving. It's going to turn out that you got to bug it, you got to influence it to cause it to begin moving. So this observation that in our universe, objects that start motionless at rest tend to remain at rest is known as inertia. It's a familiar term, inertia. It's used in common language. This is the real physics meaning of it. It's an overarching concept that observes that objects tend to remain doing what they're doing. In this case, they're motionless, staying motionless. That's the first half of inertia. There's a second half. And the second half of inertia is that an object that's in motion, so not yet, ready, now, once it's already in motion, it tends to remain in motion. There are more details coming, but that observation that in our universe, objects that are already moving tend to keep already moving, and in fact, very similar way. They do what they were doing already. That's the second half of inertia. So inertia is not a physics quantity or anything. It's just a big picture view of how things move in the absence of pushes and pulls, the influences that cause change. So skaters spend a lot of time taking advantage of inertia to keep doing whatever it was they're doing. A lot of little kids may stand around on skates doing not very much. I don't know if it's a little kid, but anybody can easily just sort of stand around motionless, staying motionless. Once you get going, you tend to keep going. Both of those are reflections of inertia. Now, inertia might sound, as I'm spelling it out here for you, like it's obvious. Of course things exhibit inertia, of course. But, in fact, in real life, inertia is not so obvious. This can, it's fine when I tip it on its side so it can roll, but this can, when it's on its end, experiences friction, it's a dirty little secret I'm trying to ignore for this entire segment. Forget friction, it's a problem. In reality, this thing does experience friction, and so when it's at rest, it tends to remain at rest. Well, so okay, that's consistent with inertia. But to make it move, I got to keep pushing it. If I stop pushing it, it comes to a stop. So inertia doesn't seem to be right at all. What's going on? What's this claim that things keep doing what they're doing? The problem is that I'm not the only person influencing this can. It's basically not free to do what it wants to do. It's suffering under friction, from friction with a table. So you got to keep pushing it to keep it moving because friction keeps acting to slow it down. Get rid of friction, however, and things keep doing what they're doing. They exhibit inertia. Okay, well, inertia is this big picture idea. Can we sort of pin it down and make rules out of it or physical laws out of it? And the answer is, yeah, sure we can. And the first of the famous physical laws associated with Newton's first law makes the following observation in a as yet primitive form. The language is oversimplified at the moment. We'll pin it down shortly. But what Newton's first law says is that an object that is free of outside influences moves at a steady pace in a straight line. So if you don't bother something, and I'm going to get it pretty much free of bother by tipping this can on its side, if you don't bother it, its motion is very simple. It moves in a straight line path at a steady speed. So right now, this is it's exhibiting that law. It's moving according to that law right now. It's free of outside influences. We'll name those influences soon. It's free of those influences, but it's not moving. And it's simply staying not moving. So it's moving in a straight line path at a steady speed of nothing, zero, boring, okay? Once I get it going, and during the getting going part, it's not obeying Newton's first law because it's not free of outside influences. I'm the influence. So I'll get it going. Now it's moving in a straight line path at a steady speed. So that's the behavior of an object that's free of outside influences. It moves steadily in a straight line. Okay? Language is simple. We'll do better. But that's Newton's first law in its first version. Can we do better? Well, to do better, we've got to start naming stuff. We have to identify physical quantities that we'll work with now and for the rest of the season here. And the first physical quantity that I'm going to want to use, and I've got 5 of them just to give you a heads up. 5 physical quantities to work with in the context of skating. The first one is a quantity known as position. Doesn't sound all that unfamiliar, but we're going to nail it down so it has a really well-defined meaning, or at least as well as I can do in these circumstances. Position tells you where an object is located in our three-dimensional world. I mean, this is a position, this is a position. Okay, this is a position. Lots of positions. How do we identify those things? And to do that, we need a couple of things, ideas. The first is we have to have a reference point to start with. We have to have something that identifies position 0, or the origin, the place where we're going to start, and that everyone agrees on. That's the 0 place. And I'm going to find something that's going to be the 0. It happens to be a baseball. Why pick something that rolls? Let me pick something that doesn't roll, like a canister. So that's position 0. And we now will identify locations, positions specifically, relative to that reference point. To do that, we need 2 pieces of information for any given position. So how do we identify the position of this can now? Well, it's about that far away from 0, from position 0. That happens to be about the metric unit known as the meter. Actually, it's a little short of a meter. That's a better meter. So that's a meter, and it's a little over 3 feet. For people who want to work with the traditional American units. So you need a distance. Distance in this case, 1 meter, because, well, I'm a physicist and you can sort of, you can live with that, okay? So the position of the can is 1 meter from 0. Not quite. That's not the whole story yet. We're short on some information here. There's something missing. The something missing is that's 1 meter, and so is this, and so is this. We've got how far away the can is from the reference point, but not in which direction. So we have to pin that down too. So the position of the can, relative to the 0 point, is 1 meter, in this case, to the right. The direction matters. The direction is a part of the physical quantity we know of as position. That means that position has both an amount, namely, in this case, a distance, and it has a direction, to the right, up, away from you. Quantities, physical quantities, that have both an amount and a direction are known as vector quantities. don't let the word vector scare you. It just tells you that it's a quantity that you can't simply type into a calculator with units, because you need to have the direction part too. It's not just a number. In fact, physical quantities are rarely just a number. They're usually a number and the units in which that number applies. So, for example, this would be position 1 inch. This is position 1 foot. This is position 1 meter, all to the right. The units matter. One of what's? One of some classic standard agreed upon amount. And for position, the amounts that we're looking for are all distance amounts. A mile, a meter, pick whatever you like, light year, all right? They're all measures of distance. In this case, it's one of them, and we need direction. It's to the right. Okay, so I've beaten vector idea to death here. Position is a vector quantity. It's where an object is located. You need the reference point, and you need the distance and direction from the reference point. Okay? All right. That was physical quantity number 1. Physical quantity number 2 is how position is changing with time. What's that? Well, it's called velocity. Another word that you may well have heard about and used even, and it has a very specific meaning in physics. It is the speed at which you're moving and the direction in which that motion is occurring. For example, here is, can I do this? Let's see. I'll do 1 meter per second is pretty fast. I will disappear from view really quickly. So I'm going to go 1 foot per second, and I'm going to do it to the right. 1 foot per second. Here we go. This is a velocity of 1 foot per second to the right. Okay? And this is a velocity of 1 foot per second to the left. Direction clearly matters. Velocity and speed are often used interchangeably in common language, but that's not right in physics. In physics, speed refers to how fast something is moving without any reference to direction. Who cares? This is 1 foot per second. This is 1 foot per second. Who cares which way I'm going? Okay? Velocity is added information. It's speed and which way you're going. So, in other words, velocity is the speed is the amount part of velocity. In the same way, the distance was the amount part for position. Incidentally, to a physicist and a mathematician, the amount part has the fancy name magnitude. The magnitude of position is a distance. The magnitude of velocity is speed, is how fast you're moving. Okay, so a skater that is moving like this is moving at 1 foot per second to the right. And how do where's a 1 foot per second? What does that really mean? It means that every second their position shifts by 1 foot. And it shifts in the rightward direction. So it's all self-consistent and hopefully makes sense. And with that concept of velocity now, we see things moving, we can pin down Newton's first law of motion fairly nicely. We're still not quite there, but we're better. And what Newton's first law of motion says with using the word velocity is that an object that is free of outside influences moves at a constant velocity. What's constant velocity mean? Constant velocity means that how the position is changed with time never changes. It keeps doing making the same shift every second. So this is constant velocity. Not yet. Right here we go. This is constant velocity. I'm moving 1 foot to the right every second. Okay? So that is consistent with how things move when they're inertial, when they are following the concept of inertia, and they can only do this in the absence of outside influences. They move at a steady pace in a straight line. That's constant velocity. Incidentally, before I forget to do this, to see position, you only have to look once. So this is one of my shticks here. It's like, is to think about how position works. For position, you only have to glance once. Flash photograph, I'm here. Flash photograph, I'm over here. You can measure position in a single burst of light. Okay? You can't do that for velocity. For velocity, you have to look twice. You have to look once, now, and you have to look again, now, to know that, oh, my position changed with time. From there to there, it occurred during a period of 1 second. He moved 1 meter in 1 second. He has a velocity of 1 meter per second, and it happens to be toward the right. So 2 glances for velocity. We'll come back to that because there's a physical quantity that requires 3 glances coming down the pipe. All right? So we've got 2 physical quantities so far, position and velocity. Well, what about those outside influences that we're outlawing in order to have Newton's first law? Those outside influences, they are the pushes and pulls of the world. So, for example, let me get my origin out of here for this second. This can sits here motionless when left alone. If an outside influence comes along, things may change, and those outside influences, which will involve my hand, involve pushes or pulls. The fancy physics name for a push or a pull is a force. And the word force shows up all over the place in movies and such. This is the real meaning of the word force. It is these influences that take you out of inertial motion, the motion described by Newton's first law. They are the influences that cause a different kind of motion. And forces are yet another vector quantity. Oh, what does that mean? A force is both how hard you push or pull and in which direction you push. A force to the right is different from a force to the left, even though they're equal in strength, equal in amount. So when you look around you at the world of forces pushing and pulling on things and how hard you push, how hard you pull, which direction you push or you pull, these all matter. They all finally come down to forces. And so for a skater to stop being inertial, to change from being motionless and staying motionless or moving at constant velocity, they need something to exert a force on them. Okay, so using the word force to describe or to identify the forces, the influences, the influences that show up in Newton's first law, that law can be restated now in its final form. That an object that is free of external forces, outside forces, moves at constant velocity. There it is. That's the whole story. That is the coasting motion of skaters, of so many objects in everyday life that are free of anything pushing on them. It's a little tricky to get free of anything pushing on you. You got to get rid of friction. You got to get rid of air resistance. You have to get rid of gravity, or at least cancel it. There are a lot of things that mess up the simplicity the simple motion that you would see in the absence of those messy forces. But if you could get rid of them, you'd see lots of examples of things coasting along. In fact, the word coasting means exhibiting the motion that is described by inertia. So a coasting object is one that is free of outside influences, and specifically free of outside forces. Now there's one little detail that I'm sweeping a little under the rug here. Well, I got to bring it up in any case. And that is that if 2 forces are simultaneously acting on an object, like my right hand is pushing the can to the right, as viewed by you, direction is a mess here. My 2 hands are pushing in opposite directions. How's that? The can can't be influenced by the individual forces. Instead, it's influenced by the sum of the forces where direction is taken into account. And so 2 people grabbing hold of a friend who's on skates and both the 2 friends pulling on the skater are pushing on the skater moves according to the sum of the two forces acting on the skater. And that summing process is not trivial. It's because it involves amounts of force and in which way the forces are, and the forces can act in the same direction or they can act opposite one another and partly cancel. It's a bit messy, and we could get lost in it forever. But the concept is known as net force, the sum of the forces where direction is taken into account. So, in Newton's first law, bring this back. Where does it fit? In Newton's first law, an object that obeys Newton's first law, that is inertial, that moves at constant velocity, is one that has a net force of 0 acting on it. It doesn't have to be truly free of all outside forces. It just has to make sure that if it is experiencing any outside forces, they sum to 0. They cancel each other out. Right? So, that's the world of inertial motion. And that's the world the skater lives in much of the time. The skater actually is experiencing gravity down. And we haven't gotten there yet, but they're being pulled downward by a force due to gravity. It's secretly known as their weight. And that by itself would cause trouble. However, the ice or the sidewalk is pushing up on the skater just as hard and is making sure that the skater experiences net force 0. Ha! The skater then moves according to Newton's first law at constant velocity. All right, well, what if you don't move at constant velocity? Well, if an object that is experiencing a net force that is not 0 doesn't move at constant velocity, they do something else. They accelerate. Acceleration is the fourth physical quantity I'm bringing up today, and sorry about this, it's another vector quantity. It describes the change of velocity with time, how your speed and direction of travel are changing as time passes. So to illustrate acceleration, let me show you, make myself accelerate. I am going to accelerate towards your right. And I'm going to start at rest, and if I were not accelerating, I would continue at rest. Velocity 0, velocity 0, velocity 0. It's constant, boring, but constant. Instead, I'm going to accelerate to your right, and I'm going to do this with the help of the floor. It's going to push on me with friction. So that's the secret underlying this, how I'm doing this. But I'm going to begin to accelerate to the right, and I'm going to do it very gently because otherwise I'm going to disappear from view quickly. So I'm going to accelerate to the right, and that means that I start to develop a rightward velocity, and it gets bigger and bigger and bigger and bigger. So I was accelerating the whole time once I got started. And as a result, my velocity is initially small, and then it's bigger to the right, and bigger to the right, and bigger to the right, and bigger and bigger. Off I go, out of view. So that's acceleration. It has an amount, magnitude, which is how rapidly the velocity is changing with time, how much the velocity now is different from the velocity now. It also has a direction. Acceleration to the right, like this, is quite different from acceleration to the left. Right? Another interesting observation is that if I am moving to the right, which is to say I have a velocity to the right, but I accelerate to the left, watch what happens. I'm going to accelerate to the left, which means I'm going to acquire more and more leftward velocity. But I'm going to start with rightward velocity. So before the story starts, let me get going. Here we go. Okay, I'm already going. I'm now going to accelerate to the left, which means I lose my rightward velocity, and I momentarily come to a stop, and then I start gaining leftward velocity. And off I go out of sight. So acceleration and velocity don't have to be in the same direction. Directions matter, and if you are moving in one direction, which is to say your velocity is that direction, and your acceleration is in a different direction, you're gonna evolve. Your motion's gonna make a transition of some sort in order for you to start begin to have more and more velocity in the direction you are accelerating. Right? Now I promised that there would be a three-glimpse physical quantity, And that 3 glimpse physical quantity is acceleration. To see acceleration, you need 3 glances. You need only 1 for position. Here I am. You need only 2 for velocity, here and here. But for acceleration, you need 3. I'm here, and I'm here. So between the first pair of glimpses, you saw how fast I was moving in which direction, so you could figure out my velocity. And between the second 2 glances, you could see which direction and how fast I was moving later on, after the acceleration had time to cause things to change. So 3 glances for acceleration. Well, what causes accelerations? The answer is forces. Again, the fancy name for pushes and pulls. If you push or pull on something and there's nothing else involved, you will cause that thing to accelerate. So forces are the cause of acceleration. There is, however, a resistance to acceleration. It's got a name that's also familiar to you, and it is our 5th and final physical quantity. And happy, it's not a vector. It's just an amount. The quantity I have in mind is called mass. It is an object. Mass measures. It's the measure of an object's inertia. Or I also think of it as an object's resistance to acceleration. How hard it is to make the object accelerate. So this object, this can, has a certain mass, and to measure that mass, conceptually, I'm not going to make it, get it to 3 digits. The way I do it is I make it accelerate. I'm going to make it go from heading to your right to heading to the left. That involves big accelerations. So its velocity goes, it's rightward velocity, leftward velocity, rightward. The shaking process, which I'm doing now, shaking something, is effectively observing the mass. How hard is it to get it to change its velocity, to accelerate? And the answer in this case, not too bad. It's got a certain mass. And the classic unit of mass that we even use in the United States is called the kilogram. A kilogram, it's not a weight. We'll get to weight later. Weight has to do with gravity. This has nothing to do with gravity. We could get rid of gravity altogether in our universe, and you'd still have mass around. It's how hard it is. Pick a bunch of skaters, a little kid. You shake them back and forth. I mean, of course, you get arrested, but you shake them back and forth, and they're easy to make them accelerate. Get some big burly person, really hard, okay? It's a little bit like, I don't have a big burly person to shake around, but I do have a lead brick. And I don't know why physicists love lead bricks, so I've got a lead brick. And this sucker has a lot of mass. When I try to shake it, it shakes me, which is also an interesting observation. It makes me accelerate quite a bit. So this has got a huge mass, and not so much, okay? So, given the idea that you have forces, which you can measure, and you have mass, which you can measure, and you have acceleration, which you can measure, there's a relationship between them, and it's an exact relationship, and it's called Newton's second law of motion. And in my preferred version of Newton's second law, it reads as this. The force exerted on an object, and actually it's the sum of all the forces, so it's the net force on the object, divided by that object's mass. So net force divided by mass is equal to the acceleration of the object. The object accelerates in response to the force opposed by the mass. So the force is the cause, the mass is the resistance to that cause, and the acceleration is the consequence, the result. So you double the net force on an object, you double the acceleration. You double the mass of the object, which is you can't do you have to change the object. You pick an object that's got twice the mass, yet you have the acceleration. So the identical pushes on a bunch of skaters, the low mass skaters will accelerate dramatically. The high mass skaters will accelerate much less. So that's Newton's second law of motion, and it applies everywhere. To everything you push on stuff, if you exert a net force on them, they accelerate in accordance to the force you exerted, the cause, and their own mass, the resistance. Now, Newton's second law is often rearranged algebraically to get rid of the division. So nothing divided. There's no division sign. Unfortunately, I don't like this form of Newton's second law because it mangles it puts cause and effect and jumbled together. So the F equals ma, force equals mass times acceleration. I mean, that relationship is still true, but what causes what? It's kind of a mess. So the point is that forces cause acceleration. The acceleration is exactly proportional to the force, and the constant of proportionality is associated with the mass. That's how much the object resists acceleration. So when you watch skaters zipping around the ice or on the skate park, when they're going straight, the net force on them is 0. When they're going straight in constant velocity, their net force is 0. When they are turning or when they're speeding up or slowing down, something's pushing on them. They're experiencing net forces other than 0, and they're accelerating as a result. Last bits and pieces of things to mention. One is the idea of a frame of reference. I've talked about all this motion here from the point of view of people standing still. You are effectively standing still because you're watching this video and presumably the computer or whatever you're watching it on is not moving. But if we were all working in a train, we would all see the same story. But someone standing outside the train would look in and watch and see, they would see everything happening. But even the things that I claim are at rest, like this, suppose that we're watching a video on the train, you're sitting on the train watching the video, and the person looks in and the stuff is all moving. So even the can that's at rest isn't at rest, it's moving. Well, how do you deal with this? Well, it turns out that there are many, in fact, an infinite number of possible frames of reference, points of view from which to watch the world. And as long as those points of views are ones that are themselves inertial, they are themselves coasting, they are not undergoing acceleration, their views of the world are just fine. And everything they see about the world moving, the motions of the world, it's all consistent with Newton's first law, second law. It all works out. So how do you do this? Let me try to illustrate this so that what I just said is clearer. For you guys, this can is motionless, I'm motionless, everything's very simple here. This is an object at rest, staying at rest. But now, from my point of view, while I'm doing that, while I'm moving along, it's still an object at rest, staying at rest. Right? You can believe that. I look over there, it's not moving relative to me. Looks the same. Right there, it's right there. So from my inertial frame of reference, and I was moving at constant velocity, I was not accelerating, well, during the meat of the story. From my point of view, it's an object at rest, velocity 0. From your point of view, and you're also sitting still, presumably, in an inertial frame of reference, it's a can that's in motion and maybe at 1 foot per second to the left. So your opinion about this is fine, and if you do all the mathematical calculations of motion, whatever you like, using your frame of reference, and you're going to want a 0.0 and all that stuff. It's all good. In mine, I got to keep them all moving. Okay? So if I do all my little calculations and measurements, all can be self-consistent too. What we compare between the two of us, we have to be careful. But in your frame of reference, everything works out. In my frame of reference, everything works out. When we talk about our different observations, we're going to have some things that are complicated. But that you don't need to worry about that. The point of this, bringing this up, is that there are often very simple frames of reference in which to observe motion that make everything very simple. For example, if we want to watch a ball going up and down, up and down, up and down, the motion is very simple. If I'm not moving, you're not moving, we're in the same inertial frame of reference. But if I'm moving relative to you, To me, the ball is going straight up and down. But to you, it's traveling in arcs. So you can see there are times when picking the right frame of reference and thinking and working in that frame of reference makes life simpler. And we'll do that from time to time. Okay, so frames of reference. The last thing to mention in this section is to take a peek at units. Units are very important because most of the physical quantities in our world have units involved in them. There are amounts to them that other than just numbers. The number 4. If you are cooking, for example, and the recipe calls for this much flour, they can describe it in various ways. They cannot describe it with a number alone. They can't say 17. Use 17 flour. What's that? Instead, they have to say, well, use 2 pounds. The pound is a conventional unit of flour or of anything. So if you use two of those pounds of flour, you've fulfilled the goal. But there are other units that describe amounts. I'm chuckling because I picked one that's fraught with peril because the pound is a complicated unit. Sometimes it refers to weight. Sometimes it refers to mass. We'll get messed up. What's a safer unit? This. I think. Yeah. This is a 32-ounce container. You fill it with water, it will contain 32 ounces. That would also be 32 ounces is about 600. Yeah, it's several hundred cubic centimeters. It's a measure of volume, basically. And you can measure volume with many different units. Cubic meters is a unit of volume. A liter is a unit of volume. A quart is a unit of volume. But anyway, the point is that once we have agreed on a set of units, if I say 4 quarts, you know what I'm talking. The world around will know what I'm talking about. They'll be able to come up with 4 quarts worth of something. And that's true for the 5 physical quantities I introduced today. Position has units. They happen to be units of length, of distance. Things like meters, inches, miles. Velocity also has units. They happen to be units of distance per time. That is meters per second, miles per hour. That's for the speed part of velocity. Acceleration also has units. They're a little more unfamiliar. The units of acceleration are meters per second, or simply meters per second squared. That's how the velocity is changing with time. The units of force also have standard units. In the conventional system we're so familiar with, pounds. Pounds is sort of the American unit of force. In the metric or SI, System International system, the classic unit of force is what's known as the Newton. The Newton is a force it's less than a pound. It's about how hard a small apple, to make it memorable, Newton, apple, ha ha ha. It's about the force a small apple exerts on your hand when you hold the apple up. So that's about a Newton of push, Newton of force. And the last unit, physical quantity, mass, has units. The classic unit of the mass, the SI or metric unit, is the kilogram. There are other units of mass, but let's leave them all in the dustbin of history. The only mass unit that really matters in modern life is the kilogram. And that's a certain amount of resistance to acceleration. So with that, then, we can look back at skaters. Skaters spent a lot of time moving inertially. That is, moving according to Newton's first law of motion because they are experiencing zero net force. When they are moving inertially like that, they are coasting. It's the same, more words for the same idea. On the occasions when they are not moving according to Newton's first law of motion, that is, when they are experiencing a net force, now they accelerate, and they accelerate in accordance with Newton's second law of motion. Their acceleration is equal to the force exerted on them, the net force, divided by their mass. And so they speed up, they slow down, they turn, and all that. And that about does it for the topic of skating.